My topic is artificial intelligence that can imagine. We think that's the future of AI, and that's the kind of thing that we are developing at the Curious AI company. We have been talking about some other things, but now this is the first time I'm speaking about it here. Antti Rasmus gave a very similar talk in Tallinn last week, so if you saw that, apologies for that. But anyway, the context here is that, as you know, deep learning has done really good job at fixing some problems, the remaining problems that we had when developing real-world systems. It has been making really good job in that kind of problems where you need to understand real-world data, images, text, speech, and all kinds of complicated data from the natural world. So it is really big and important. There have been huge improvements after deep learning started really working. But there are also some remaining problems. So it's not the real AI just yet. So if you try to apply these techniques, this deep learning in the real world, there are some a number of problems. One of them is that you still need to have a lot of human work there. You need to have a lot of labeled data. So that's time consuming and costly. Another thing is, on top of that, you still also need to have huge amounts of data. So not just labeled data, but any data. If you compare with human learning performance with deep learning performance, we humans are much more sample efficient in many tasks. And this problem of needing lots and lots of data, we can break that into two different problems, I think. Also why we need a lot of labeling, that can also be broken down. But one reason why we need so much data is our current systems still make pretty poor use of causal models. And that relates to the topic I'm going to talk today. And then another thing, deep neural networks have pretty poor understanding of objects. So they are bad at generalizing to new kinds of situations. So of course we have already started to have solutions to these problems. So we have been presenting here, and also others from NVIDIA, even in these AIHelsinki meetings, we have been talking about semi-supervised learning. And that's at least a partial solution to this needing a lot of human labels. Then poor use of causal models. Internal simulation will help there. I'm going to talk about that shortly. And then this poor understanding of objects. There already are some object interaction models that even I talked 1.5 years ago here about Tagger network. This is not yet completely solved problem. So AI still doesn't understand kind of structured data that we have, but we are getting there. So we know roughly what kinds of solutions we should have in each one of these problems. We've been working on this. So today I'm going to concentrate on this internal simulation, what it can do. Why does it lead to needing less data? Many of you know already about AlphaZero. There was AlphaGo, which first beat Lee Sedol almost 2 years ago now. And it played the game of Go. Now AlphaZero also extended this to chess, and the Japanese chess. I forgot what was the name of that game, but so it seems really good. It's beating humans. So let's have a look at why it works. And one crucial point about AlphaZero is that it doesn't need human labeling. There's almost no human work needed to program that. So it seems to be an interesting solution. Let's see how it works and then extend from there. So the way it works is that you have some kind of game state, and then you know that you're supposed to make some moves in the game, controls in some sense. You are controlling the game, and then you have some kind of goal in the game. You want to humiliate the human, obviously, if you're a game AI. So the way AlphaGo works is that it's simulating, kind of imagining a lot of games and figuring out how to get to the end state. So any chess program will do this. So there's nothing particularly new about this kind of simulation. But in deep learning and so on, that's kind of new. And yes, it works well. It beats humans and without any label. So basically, after 0 labeled samples of games, it has never seen anybody play the game. It's still able to beat the human at first exposure to real games. How does it do that? In some sense, this AlphaZero has 2 modes of thinking. One of them is this kind of simulation or self-play. AlphaGo knows the rules of the game inherently, and then it starts to simulate games. And these simulated games then teach another system, like this kind of simulation that's very slow, and you would never be able to beat a human just by doing that simulation, except that now there's a second system which is learning, and that uses deep learning. So this deep learning system is taking the results from the simulation system and then learns to predict how will that planning, what are the results of the planning. It learns to evaluate the game board situation, like given this state, how likely is it that I'm going to win? And it gets that data from the self-play. Also, it learns to predict what are next good moves in this situation. And again, it gets that data from the self-play. So self-play is slow, but then it can provide target training data for the neural networks, which then learn, and then by learning make this self-play faster. Because then while the system is learning to evaluate the board positions and learn to predict what are good moves, it will make the planning process much more efficient. So internal simulation is one thing, and you could build a system which relies only on that. And then there's a second system which learns to make shortcuts in thinking. And this is something which you could train on human game playing. You wouldn't need to have this self-play system at all. But when you combine these together, you get a very, very efficient AI. Now, if we look at humans, I hope some of you have read Daniel Kahneman's excellent book, Thinking, Fast and Slow. It talks about these 2 systems that you find in the brain. And people have identified the system 1, which is like autopilot. It makes very rapid evaluations of situations and very rapid like reflexive movements, it learns habits. And then there is this system 2, which is slow, planning-like thing. There is sequential thinking going on there. And this is a system which is very flexible in the sense that when you get into new situations, you're able to use that. And now I hope that you kind of already see the pattern. So obviously this system 1, this autopilot, which is a little bit like sleepwalking or zombie mode, that's how most deep learning systems now work. That's what deep learning learns. Input-output mappings. And in current AI systems, this system 2, this exception handling, is something that either humans have to fill in that, so humans provide all the data, and so humans do the thinking and then provide all the labels. Or in the case of AlphaGo, humans did something there. So, okay, AlphaGo is doing this, so is that everything? Unfortunately not. The problem is that in AlphaGo, it's not generic. It's still narrow AI. It's not general AI that we would like to build, because the rules of the game are inbuilt. AlphaGo can work only because the rules of the game are so simple. There is a finite set of simple logical rules in this game. So you can build this kind of game simulation engine. So now if we would like to apply this same principle in real world, so let's take some kind of robot dog, for instance, and try to see if it could start playing football. Actually, in robotics, people normally, the way they do robotics is that they do have the internal model of the robot. They know exactly that if we move the robot joints into these angles, that's where the robot hand will be. And then they invert that. So they are using this forward model. But the problem is that if you want to do anything more complicated, anything which interacts with the real world, footballs or humans or basically anything, then it's very, very hard to just build in that model. So the trick to solve this, obviously, is to use deep learning not only to learn those shortcuts of planning, but also to learn the rules of the game. How does the world work? This causal forward model of the world. So works like charm in principle. So imagine that you found somewhere an excavator. You don't know how it works, but it has these handles, many different handles, and what you can do with the excavator, particularly if you're a child, I know that young boys, for instance, if they would find an excavator like that, they would immediately jump in and start pulling the levers and see how it works. So just by trial and error, you can learn the rules of the game. You can learn to predict. So then you see that, okay, if I move this lever, this arm of the excavator is going to move. And you can build a predictive neural network model out of that. So, very simple. And all we have to do then is to do planning, right? So in order, if we have a goal in mind, so I would like to have a big hole in here, what should I do? Then you just apply this same principle, right? Well, there are two small things that still need to be solved, and I hope I have enough time here to go into more technical detail here. I think I do, right? Yes. So first problem that you run into these kind of things is that while in the game of Go, for instance, the games, they are kind of long, but it's still like 100 steps or a few hundred steps. But if you think of some real world problems that you face, for instance, fixing a dinner, and then if you think of muscle movements and so on, how many muscle movements you need before you have a dinner? And dinner is just like for today, but what if you have to figure out how to make nice career moves? It could take a decade or something. So nobody plans a dinner party one muscle movement at a time. Nobody. That's just not feasible. So there is a fairly obvious solution to this. I'm not going to talk too much about that particular solution, and it's not needed in simpler problems like AlphaGo. Or AlphaZero doesn't need this thing. But there's a solution to this, which is hierarchical models. So rather than just roll the future plan like one muscle movement at a time or one move at a time, use bigger chunks which have bigger or longer time intervals between the things. So rather than think of muscle movements, think of bigger things like, okay, I'll go to shop, then I'll buy all the ingredients, then I'll go home, maybe I should invite my friends. So all of these are actually very broad, high-level descriptions of a long sequence of movements. And when I'm doing planning, I'm planning at that higher level, which means that I do not need to roll my plan on the short time interval thingy. So that's kind of obvious. And this is something that people have been working on, we've been working on, but that's unfortunately not still enough. There's another problem which is related to neural networks and optimizing the inputs of neural networks. You may have seen some panda gibbon images before. So pretty famously, neural networks they are very good at classifying stuff. So suppose we take a neural network that has learned to classify all kinds of animals and so on. This particular one has been trained with ImageNet dataset. Now, you might hope that you take this neural network and suppose we want to find an image of a gibbon. So we could ask a question, how should that panda image be changed in such a way that this neural network would then consider it to be a gibbon? And when you try to do this, completely miserably fails. This was some years ago, this was a revelation to people that, wow, this actually absolutely doesn't work. So that panda image there has tiny little changes compared to the panda image above. So it's like panda plus some funny pattern, which is not perceptible at all because it's such a small change. But this neural network, after this funny change, will think this is a gibbon. And the way this happens, when you take a neural network and you ask it to produce a gibbon and you ask it what kind of how to change its inputs, you can use backprop or something to figure out how to change those inputs, and then you will do that. You notice that very small changes will give you this gibbon. This is related to our planning problem, because what we have here is that we have this neural network that can predict forward. In this state, if I do these movements, that's where I'm going to end up. But what you have is you have a goal state. You know what you want the neural network to give you, and you're looking for the inputs, the correct inputs. What kind of controls should I put in so that I get my nice whole? And it gives you, if you try to do this optimization, it gives completely delusional plan. So the neural network will think that with this funny plan, you will get a hole in there. and then if you try it, it just completely miserably fails. So now, even more technical detail. Why? So that's by the way the panda image plus very, very little noise, and then it's given with way more confidence that it ever had about the panda. Now the problem here is that when you try to do this kind of gradient change, what happens is that you push the network outside of the learned manifold. So the neural network is perfectly good for all the natural images, but if you ask it to produce a particular image, then it will give you something else, and it doesn't know what these are. So there is a very clear solution to this also. Ask the neural network to stay on the image manifold. We have to learn that image manifold separately, and that's what we have been doing. For instance, we have been using the ladder network. There are other solutions, other types of networks that could be used that learn the input statistics. What is this manifold? And then when we regularize this optimization or inversion process, it works nicely. So we use this ladder because denoising function gives us the gradient of log probability like for free, and we can directly plug it in. I'm not going to go too much into these details. There are actually some papers already, like from more than a year ago. People know about this connection. So this is one way of doing it, but one way or another, what you need to do, you need to take into consideration what is the statistics of your inputs, not only the outputs. So here's an example. On the left, there is an inversion process going on MNIST digits. So we've trained a fully connected network to classify MNIST digits. On the left, there is just the encoder, which is like normal feed-forward neural network. And on the right, this process is regularized by ladder network. So each row here is one iteration, and each column here is one target. So here the target is 0, 1, 2, and from far away you can actually see that there are these digits, but when you come close you see that these are completely blurry. It's very, very noisy, and from close you wouldn't recognize these. On the right, they are nice images. Even if you go close, you see that they are nice smooth images. If you take another initial point, you will get a different local optimum. And then if we train another network which sort of learns the generation process directly, in connection to control, this would be called the policy network. The network that learns at this stage, if this is the goal, that's what we should do. Then it gives really, really nice MNIST digits right away. So with this process, we can really reliably invert neural networks. And now, when we apply that to control, we get, well, it kind of works. So I'm going to show you a simulation of a four-legged robot that's part of OpenAI. Is it Jim or like OpenAI Jim? Antti Rasmus here has made all these simulations. So if you have any questions about this, you ask him. So initially, you just make these random movements. So it's like boy at the cockpit of the excavator for the first time. You just make some movements and see what happens. But there is a goal also for this creature. It wants to move forward. So pretty soon it will learn how to move about. And in 45 minutes is really good. It doesn't get penalized by straying off the track as long as it's moving in that general direction. So it's not moving, not staying on the track all the time, but that's not the point. So the point here is that this kind of learning is really sample efficient. Like AlphaZero needs 0 samples from real world play. This does need samples, obviously, because it needs to learn the rules of the game. But once it's learned the rules of the game, it can deduce many more facts from it. And if you take model-free reinforcement learning approaches, you would have to learn each and every case separately. So now in this case, when we learn the rules of the game, then by internal simulation we will be able to generate more training data in some sense. Right, so we are applying this to, not for gameplay, some people might be interested in that too, but for real world problems like controlling industrial processes. Some part of the model can be derived from physics principles, or some engineers have derived some parts of the model, but there are always, in a big process, things keep changing and so on. So it's very good to have neural network to learn also that part of the model. Another thing which is, I think, maybe even more interesting is to learn, for instance, human behavior. If we want to build computers, and we do want to build computers that can work with humans, we better understand how humans work, for instance, how our emotions work, what are our goals. If I do this, then the human will be happy. If I do that, then the human will be unhappy, and so on. So very similar principle. We learn how to make somebody happy or angry, depending on what you want to achieve, and then you can, based on your forward modeling, you can figure out how to behave in all kinds of situations, not only the situations that you have encountered, but also new ones. So far I've been talking about action, and the deep learning version of that would be that we train a neural network that given an input state, try to predict the output, try to predict the control signal. For instance, for a self-driving car, this would be obvious, like if there is a car coming my way, I need to turn the wheel this way, or so on. This same principle also applies to other problems like perception and communication. So let's take perception first. Neural networks are used for classifying or recognizing things all the time. And typically the way you train it is to give input-output pairs. Like, this is number 3, or this is a dog, and this is a panda, and so on. You give input-output pairs. If you get a new input or new image that wasn't part of your training data, maybe not even part of your label set, then you're out of luck, typically. But humans, we can use internal simulation again in a kind of Sherlock Holmes mode. You know, Sherlock Holmes comes to the place of the crime scene and sees a scratch in the floor and maybe some lipstick in the mirror, and then starts simulating the past. So what has happened in the past? And then we'll be able to pick the simulation that matches with the observations. This is exactly the same principle as we just discussed in making decisions, except that in planning, you simulate the future, and then you select the simulation that matches your goal. while in analysis and perception, you simulate the past and then you select the simulation that matches your observations, right? So you may have now had an image of Sherlock Holmes getting to the crime scene and so on. If you did, then I was playing a trick with your brain. And that's what communication is about. Communication is fundamentally about transmitting one simulation from one brain to another brain, right? So there, in communication, when I'm trying to tell you something, I have something going on inside my head, and I try to elicit that same image, same simulation in your head. So you could say that decisions are simulations of the future, analysis is simulation of the past, and communication is transmission of these simulations. So this principle, we believe, will be very important, not just for making computers that can make good decisions. It's also a way to get computers to really understand stuff properly, analyze stuff properly, and to talk about it, communicate with people. And that's really important. We need to get computers able to work with humans, not just have black box solutions that do whatever stuff they do and don't touch it, kind of thing. So we are building these AI co-workers now that work alongside with human, learn what the processes are about, what are the rules of the game, and that's the future of AI. Thank you.